All right, let's take a look at another graph column, flight discount. So what's going on here? We want to find a minimum cost flight from Surjala to Metsala. We have a discount coupon, so we can have the price of any flight. We can only use that coupon once. So this is sort of the gimmick here. And other than this, it's a normal shortest path problem, right? We have n cities, vertices, m edges, flights. We want to get from 1 to n. And we have a bunch of directed edges, right? Unidirectional, one direction. Flights from A to B with a cost of C. We can assume that it's possible. That's nice. And we just want to output the length of the shortest path. It's also nice. And the discount coupon halves the price. And if it's odd, it gets rounded down. So that's nice too. And there's 100,000 edges and 200,000 vertices. So this, as you might be able to guess from the constraints, is just a straight Dijkstra problem, actually. But if it wasn't for the coupon, like the discount coupon, this would definitely just be Dijkstra. The discount coupon, we have to handle that somehow. So how can we do that? So it turns out that there's a nice way, which let me show you what that is. So I've drawn out the sample input. And so here, I believe the answer is 2, because you can use the discount coupon here to reduce this cost to 1, and then another 1 gets you to 3. That's what they say, so that's nice. So how do we model this? And so the answer is that you make another copy of the graph. So this over here is going to represent coupon when we had the coupon. And over here is going to represent that we've used the coupon. So yeah, we make another copy of the graph, entirely the same as the original copy. This is 3 cost, this is 5 cost. And now we draw in edges between them, which represents using the coupon. So this 7 edge becomes an edge like this of cost 3, right? Because 7 divided by 2 rounded down is 3. This edge from 1 to 2 becomes a 1 cost edge. This edge from 2 to 3. I'm not going to draw them all in because it's going to be very messy. My paint drawing is already quite messy. But the point is that you make copies of these edges, all the edges in the graph, going from this section to this section, and they're all costs are all divided by 2. And so that represents using the coupon, right? So one time you get to take one of these half cost edges to the other copy of the graph. And then in this other copy of the graph, you're just normally flying around, right? So you can normally fly around in this half. You can normally fly around in this half. And one time you can move from this half to this half by using the coupon. And so this is a sort of faithful representation of the problem, right? If you think about it, of one time you get to use a coupon and take a half cost edge. And other than that, you just fly around normally. And so we can just do Dijkstra on this graph, which will have twice as many vertices, and I guess 3 times as many edges, right? Each edge appears once in this graph, once in this copy, and then once as a half cost edge between them. But that's fine. The Dijkstra is like n, I guess m log n. So anyway, just multiplying these numbers by 3 is not going to be a big problem. And notice that all the edges are positive costs, so Dijkstra will work fine. So that's it. Let's actually do it. What is this called? Flight discount. N and m. And we are going to read in the m edges. As usual, they are 1 indexed, and we are going to work with 0 indexed. So that's what this is for. We're going to keep track of the edges coming off of each vertex, as usual. This is a pair, actually, because it has both a destination and a cost. And so for Dijkstra, we use a priority queue. Right, and priority queue by default gives us biggest things. We want smallest things, so that's why we pass in greater. Normally it uses less, right, to flip it, so that it will give us the smallest paths. So what is going to be the things in the priority queue? Well, we need the first thing to be distance. The second thing is going to be which vertex we're on. And the third thing is whether or not we've already used the coupon, which we can just represent with a Boolean, true or false. So that's what we're going to have in the queue. Let's see, so initially we were at distance 0, at vertex 0, and the coupon is available. So we want dx and avail equals q dot is the top, I think. Let's see if I remembered the priority queue API correctly. Let's just do the includes now, since we're thinking about them. Priority queue is in queue. We also need tuple, stud, 64t. Okay. And oh. I'll show a slightly different way to do Dijkstra, where we'll represent unseen as infinity. Sorry, yeah, unseen or not currently reached as infinity instead of -1. This will allow us to do it this way. Okay, so if this is better than the best available distance we know about for getting to d, and update that, and for each edge coming out of x, we can go at distance g plus c just by taking this flight. We can go to y with the same availability. And if we still have the coupon, we can also take that flight at half price. In which case we've used the coupon. So at the end we want to print out the distance at the end, and we can assume that we used the coupon at some point. There's no reason not to. So that should be it. Let's see if this compiles. Does not. Yes, okay, that's fair. That did not make any sense. This is a vector of vectors. It's silly to have a vector of length 2 here, but whatever, it's fine. That does compile. And we got 2, which was the right answer. So that's nice. Cool, so that worked. Okay, so what's going on here? We're not actually explicitly constructing this graph that I talked about. We're sort of implicitly doing it, especially not the edges. Right, so we're just reading in the edges sort of normally. Right, it's a one-way flight. So this is the only, there's no edge from B to A here. So we record all the edges coming out of each vertex with their destination and their cost. And then we have this priority queue of like things to explore, which has three things in it: the distance, where you are, and whether or not you still have the coupon. And you're going to keep track of the distance to everything, starting them out at infinity. So while there's sort of, I don't know, things left to explore, grab the first thing, distance, where you are, and whether or not there's a coupon. If we haven't seen it before, right, so this distance is going to be less than infinity. Just mark down the distance, and for each edge coming out of X, or each flight, right, out of that city, we could take that flight, and if we have the coupon available, we could also take the flight at half cost, which uses up the coupon. Right, so this is sort of the representation of these edges that go into the second copy of the graph, right, and they go into it because eval used to be true and now it's false. Right, this is, whether this is true or false is tracking whether or not we're in the second copy of the graph or the first copy of the graph. And then this represents the edges in each copy of the graph, right? Regardless of where you are, you can just take the flight normally and keep, being in the same copy. So these are the edges within the copies, and these are the edges sort of across the copies. And we just need to print out the cheapest way to get to the end. I suppose technically, right, you might say, well, what if you didn't want to use the coupon? But there's no point in not using the coupon. It always makes the edge at least one cheaper since it rounds down. Even if it didn't, it would still. So anyway, it would be valid to not use the coupon, but there's no point. Like the shortest path using the coupon is always going to be better than the shortest path not using the coupon. So that's why we can assume that the coupon is false that we've used it when we're putting out the answer. And that's it. So a nice little twist on Dijkstra, right? Another application of it.